Okay, in this section, we're going to talk a lot about what's called integration by parts. It's this really cool way to integrate, but it's also a little bit tricky because you've got to really sort through kind of what's going on and pick certain things, and it can be a tough little guy. But basically, it's the product rule in reverse is what we're doing. Is we're kind of undoing the product rule here. So, and remember, product rule says if we've got like if we have f of x equals u times v, then what we have is u times v prime plus v times u prime. Okay, that's your product rule. And so what we're going to do with our product rules, we're going to set up and this is called integration by parts. We're going to pick two things. We're going to pick something to be u, and we're going to pick something to be dv. And when we do that, we follow this pattern on the right-hand side of the equal. We're going to follow this pattern right here. Okay, so let's go ahead and give this a try. And this is all pattern-based stuff. So if you don't see it the first time around, that's okay. Practice, 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 and it will make perfect. All right, so let's give it a try. X cosine x dx. There's no way that I could set a u substitution up for this and get it to work. If I let u equal x, as we've learned about substitution, when I take that derivative, du dx is equal to 1, multiply both sides by dx, so du is equal to dx. I have dx, but I also have this spare x running around. So my integral would look like this. X, it would look like u cosine u. And this is basically exactly where I started. I can't integrate this. We don't have something, a pattern or anything that this would integrate back to that we know right off the top of our heads. So what we're going to do is we're going to come back here and we're going to we're going to follow this pattern of u dv. Okay? So here we go. Let's let u equal x, and let's let dv equal cosine x dx. Okay? And the reason that we're going to do this is now when I substitute these guys in, this integral becomes the integral of u dv. Okay? And I'm picking these for a very specific reason, and we'll see later why. So I've got u times dv. So what do I need to do? I've got to get u times v. Well, I don't have v. I've got dv. So integrate this one. And v becomes, when you integrate cosine x, you get sine x. Okay. So here's u times v. All right. That's this part of my equation. So I've got u times v. So here we go. This will be u times v minus the integral. And then I need v du, but I don't have du. So back over here to this guy, take the derivative of both sides. So du dx equals 1 and du equals dx. So now I do v times du. So sine x times x dx. Sine x, that's the wrong color. Okay, so I'm going to have v du right here, sine x times dx. All right, one more step here because I can actually now integrate sine x. And so that's going to give me x sine x minus cosine x plus c, because now we're at the very end of our integration. We've got to add that constant of integration. And if you'll notice right here, if I take derivative of that, I would have to do the product rule because I have one function times another. And so this is really kind of a cool thing to work with, but it can be a little confusing. And by the way, the antiderivative of sine x should be minus cosine there we go. All right. So this is integration by parts. Some tips for choosing, okay? Some tips for choosing what needs to happen, and I put them right down here for you. All right. Some tips for choosing. Always pick natural log to be your u if that's an option. That wasn't on this first one. Then look for an inverse trig function. We also didn't have one of those. Next, look for any polynomial. That's the x. All right. If there are really no polynomials, look for an exponential function. And then lastly, look for the trig function. Notice that we did not pick trig to be u. Okay. We usually want u to be something that simplifies when we take the derivative. And we want dv to be something that kind of remains workable when we integrate, that doesn't become too horribly nasty. And I'll be honest, it's tough sometimes to pick the right thing. But if you follow this table right here, this tips and tricks for choosing u, you will generally wind up with the correct u and the correct v. Okay, but just like when we learned how to evaluate indefinite integrals, it takes practice. And so integration by parts, it takes practice. But the more you do, the easier it will be. All right, every now and then, you're going to run into a problem where you're going to have to use parts more than once. Pay attention to what you're doing. Keep track of all your minus signs, and you're going to be just fine. Now, remember how we're going to pick a u and a v right here. We're going to try and find something that when you take the u and you take the derivative, it simplifies, and when you take dv, it kind of stays the same. So let's real quick remember how this all works. U dv is equal to u times v minus the integral of v du. Okay? All right. So I'm looking for like a natural log right off the bat. I don't see one. I'm looking for inverse trig right off the bat. I don't see one. I'm looking for a polynomial for u. I see one. So we're going to let u equal x squared. And then that would mean then that this guy right here, e to the x, would be my dv. So if I substitute u in for x squared and dv in for x, my new function is going to become, my new integral is going to become the integral of u dv. Hey, we just discovered that right here. So what I need is u times v, but I don't have v, so I'm going to integrate these guys. All right? And when I integrate these guys, it's going to give me v equals, and e to the x, quite frankly, is a really nice jack of all trades, okay? When you integrate e to the x, it's e to the x. When you take derivative of e to the x, it's e to the x. So this guy's actually pretty nice to have in our problem because we can usually go either direction with him. And he's still manageable, e to the x, okay? So I've got u times v, okay, right here, x squared e to the x. So right here, x squared e to the x minus the integral of v du. Well, I've got v, but I don't have my du. So let's see if I can figure out which color I had here. So du is going to be 2x dx. Did you see what I did? Did you see what I did? I did 2 for the price of 1. I went ahead and multiplied both sides of my equation by dx right here. So now that gives me 2x dx times e to the x. All right. I'm going to have to do parts again. How come? Because this guy right here doesn't integrate to something that we already know. Okay, he stays kind of complicated. So we're going to do parts again, and we're going to pick a u and a v again, and we're going to work with the integral of 2x e to the x dx, okay? And I'm going to allow this guy right here to be my u. And if you pick dv to be e to the x, then if we have to do integration by parts more than once, always pick dv to be e to the x. All right, so now what we're going to do is take the derivative of the u. All right, so that's going to be du equals 2 dx. We're going to integrate dv. And we love this one because when you integrate e to the x, it's e to the x. All right? And so back over here now, I'm going to have x squared e to the x minus, and then I integrate this guy following my integration by parts rule. So I've got a new u and v. So 2x e to the x minus the integral of v du. v du. And now this guy is a lot easier to work with, okay? This integral right here, 2e to the x, is not bad because we can bring the 2 in front of the integral. And e to the x integrates to e to the x. We've just done that one twice already. So my next step in simplification would look like this. I don't know why my lines are getting shaky over here. Would look like this right here. When you integrate 2e to the x, 2 is a constant and it can move in front of the integral. E to the x integrates to e to the x. So what have I got for my final answer? Well, there's a couple of different ways to write this. You could write this as x squared e to the x minus 2x e to the x minus 2e to the x plus c. You could write it this way. Sometimes if you look in the back of a book or if you're checking your answer online or if you have a professor that likes to see things a little cleaner, you'll notice that there's an e to the x in each part here that you could factor out if you wanted to. I don't necessarily expect you to be able to do that, but it's something that may or may not need to do at some point. So I just point that out that there is a possibility. I'm not going to make you do it. But there you go. So there's integration by parts more than once. And the key here is this. When you have to integrate by parts more than once, whatever you pick as your dv has to remain your dv the entire way through the process. If it doesn't, you're going to wind up back where you started with your original problem, or you'll end up with a problem that just doesn't seem to go anywhere. So if that's happening with you on an integration by parts problem, double check and make sure that you're using the same dv every time you integrate. Alrighty, let's look at an initial value problem where we've got the differential equation dy dx equals x natural log x, where the initial condition is y equals -1 and x equals +1. Show your solution conforms to the slope field for this differential equation. Well, here's what you do. You graph the slope field using your calculator, and after you've graphed your slope field and worked this out, then you put into your equation as y2 or f2 the answer that you get, and it should line up perfectly with your slope field. So what are we going to do? Well, let's take this guy, dy dx. Well, we want to integrate this. So if we have dy dx equals x natural log x, and we're asked to solve this out, then we need to multiply both sides by the dx. The reason we need to do this is we need to split up these two differentials over here so that we can get an equation we can integrate. And remember, integration is nice because we can integrate both sides. And if you integrate y, you're going to dy, you're going to get y. And if you integrate dx, you're going to get x's. So let us integrate. All right. On the left, then, we have y equals. On the right, though, we've got this integral now of x natural log x dx. Now, there's no way that we could use a regular u substitution. There's no way that we could come in here and do something different. This is a problem. So what do? Well, we go to our handy-dandy integration by parts. So if I have the integral of u dv This is the same thing as uv minus the integral of v du. And we're going to do parts. How do you do parts? Well, remember, the first thing that we wanted to pick for u was a natural log. And we've got one now. We've got a natural log. So let's go ahead and let u equal natural log x. That means that du then is going to be x. I'm sorry, dv is going to be x. All right, so here's your setup. So remember, we need u times v and v du. So we're going to take the derivative of this guy of both sides. Du is equal to, and the natural log, when you take derivative of natural log, it's going to be 1 over x dx. Or another way that you might see this would be dx over x. These represent the same thing. When I take the derivative of, or I'm sorry, when I integrate, let me find the right color here. I'm having trouble finding the color I'm using. When I integrate this side, when you integrate dv, that's just going to give you v. It's not the right color, sorry. And when you integrate x, that's going to give you x squared over 2. Okay? And that's okay. That's okay. Don't panic. And so what we're going to do is we're just going to run over here now, and we're going to set up our uv minus v du part. So u times v, x squared over 2 times the natural log of x, minus the integral of v du, x squared over 2 times 1 over x dx. Now, when you're looking inside this integral, don't panic. Don't panic. Look at this. Look what's going to happen. This x down here on the bottom cancels out with one of these x's up here. So what I'm actually working on is x squared over 2 times the natural log of x minus the integral of 1/2 x dx. Okay? And that really is not that bad. So this is going to end up being x squared over 2 times the natural log of x. And then when I integrate this, it's going to be minus 1/2 times x squared over 2. Okay, kind of cool. So the actual starter, the function, the y equals for this problem is x squared over 2 natural log x minus 1/4 x squared plus c. That's my actual problem, okay? And they gave me an initial condition. Y is -1, x is 1. Well, this is my y equals guy right here. This is what y equals. Remember, we just solved that integral right there, all right? So put -1 in for y, put 1 in for x, and let's rock and roll. So when that happens, let's see, I need a little bit more space. So I'm just going to come right down here with this guy. I'm going to have -1 equals 1 squared over 2 times the natural log of 1 minus 1/4 times 1 squared plus c. All right, so this -1 where the y is doesn't change. This is going to be 1/2 times the natural log of 1. The natural log of 1 is 0, so this whole thing goes to 0, minus 1/4 plus c. So what is c going to be? Well, I add 1/4 to both sides here, and c becomes -3/4. So when I solve this differential equation, what I'm going to get is going to be y equals x squared over 2 times the natural log of x minus 1/4 x squared minus 3/4. That's your answer for this particular initial value problem. And he's not that bad. He's not that bad. He's totally doable. You just go one little part at a time, and it'll unravel itself. And you should be able to, you should know you're headed down the right path when your integrals are not too complicated after you make your substitutions for the integration by parts rule, okay? Again, this is one that you have to practice. It can be really challenging to sort these things out and pick the right u's and dv's, but again, you want to pick that u where it differentiates and gets easier, and you want to pick that dv where it integrates and stays manageable. And keep in mind those clues that we talked about on our first slide, okay? Look for natural log, look for inverse trig, look for polynomial, and work your way down that list that way, okay? All right, here we go with unknown integrals. These are sad integrals. Nobody knows them. Just kidding. They can take up some paper and they can be a little bit tricky. So these are definitely ones that where you might want to work the same integral a couple of times to make sure that you can get where you're going and not have a big mistake or issue. So evaluate e to the x cosine x. Now, let's just keep a couple things in mind here before we get going on this. So number one, if you take the derivative of e to the x, so if I have y equals e to the x and I take the derivative, I get e to the x. And if I take the derivative of that, I get e to the x. On the other hand, if I integrate all of these, integrate, they integrate to e to the x. With cosine x, if I take the derivative of cosine x, I get negative sine x. And if I take the derivative of that, I get negative cosine x. And if I take the derivative of that, then I get, negative cosine, I get sine x. And if I take the derivative of that, I'm back where I started. So both of these guys lend themselves to repeating, and no quick, easy way to get out of it, okay? Well, going back to our tips and tricks, and keeping in mind how integration by parts works, where we're going to have the integral of u times dv. This is going to be uv minus the integral of v du, okay? So while we're working on this part, remember that we wanted to pick u in very specific ways. Something where you took a derivative, it generally got easier, and something where you integrated, it generally didn't get much more difficult. So what to do here? Well, in our tips and tricks, one of the last things we wanted to pick to be u was a trig function. So in this case, we're going to let u equal e to the x. It was actually one of the ones that we wanted to try and use as a u. And so that means that dv is going to be cosine x. All right? So here we go. U equals e to the x, dv equals this. Integrate u. Take derivative of u and integrate v. Hello, Sports Center. All right. So here's our initial setup. Okay, and what we're going to do is we're going to do our uv integral v du. So u times v, that's going to be e to the x sine x. Okay, minus the integral of v du. So that's going to be e to the x sine x. All right, so we can't integrate this guy either because we're basically the same place that we were right here. So we're going to do parts again. U is going to be e to the x, so du is e to the x dx. Dv is going to be the sine of x this time, and dx. So when you integrate sine of x, you get negative cosine x. So we're going to set that guy up the same way. So here we go. By the way, this is y equals. So now y is going to equal e to the x sine x minus, and looky right here what we've got. We need u times v So that's going to be negative cosine minus the integral of v du. And looky here, we're minus e to the x cosine dx. All right. Well, now what do you do? E to the x cosine x, that's basically back to this guy, which is where we started. So what's going on here? Well, let's write it out and simplify it just a little bit. Y equals e to the x sine x minus negative e to the x cosine x plus the integral of e to the x cosine x dx. Can you see that we would keep going and keep going and keep going with this guy? We'll take one more step.
Do you want cherry?
Sure, I'll take cherry. Oh,
I tried.
all right, that's okay. Good toss.
Not in sports for a reason.
That's all right. Okay, so to wrap up this question, I'm just going to make a small change here. I had to pause for a second, and I noticed these aren't y equals, by the way. Remember, when you're doing integration by parts, you've got this integral equaling this stuff. So for my integration by parts, my integral is equaling this stuff. So this is the integral of e to the x cosine x dx all the way down. So this is the integral of, all the way down right here, all the way down right here. So what we're going to do is clean up one more step on this guy. E to the x sine x minus, plus e to the x cosine x minus the integral of e to the x cosine x dx. Now, remember what this equals. This equals the integral of e to the x cosine x dx. And notice one more time that this guy and this guy are exactly the same. So if we want to know what that integral equals, we can actually move this whole thing over by adding it to both sides. And when we do that, we get a brand new thing. We get 2 times the integral of e to the x cosine x dx equals, and then on the other side, we've got this e to the x sine x plus e to the x cosine x. And then if we divide all of that by the 2 right here, and add a c, we've got our integral. Because then when you look at the integral of this guy, e to the x cosine x dx, that is this answer inside the box. All right. So there's a few steps to take on this, and some of these can take up some paper and some space. But again, these are ones that if you practice just a little bit, you should be able to get to where you can get to the end and find where your integral starts to repeat itself so that you can simplify it.